All right, let's go.
Number 8. The Bohr Model. The picture everyone learns. The picture that is wrong. Every science textbook on Earth still shows you the same image. A tiny solid nucleus at the center. Electrons circling it in neat, fixed orbits like planets around a sun. That image is called the Bohr Model. Niels Bohr proposed it in 1913 to fix a problem in Ernest Rutherford's earlier nuclear model. Rutherford had shown through gold foil scattering experiments that atoms have a tiny, dense, positively charged nucleus with electrons somewhere around it. But classical physics said that an orbiting electron should continuously radiate energy and spiral into the nucleus in a fraction of a second. Atoms should not be able to exist at all under classical rules. Bohr's fix was radical for its time. He proposed that electrons can only occupy specific, fixed energy levels, stationary states, and cannot exist anywhere in between. An electron can jump from one level to another only by absorbing or emitting a photon with exactly the right amount of energy to match the gap. This explained with remarkable precision the specific colors of light that hydrogen atoms emit and absorb, the hydrogen spectral lines that had puzzled physicists for decades. It was a genuine breakthrough. It also broke immediately outside of hydrogen. The Bohr model could not correctly predict the behavior of any atom with more than one electron. It could not explain why some spectral lines split into multiple closely spaced lines under a magnetic field. It described electrons as tiny particles following defined circular paths, an image that later physics would show is simply not how electrons behave. The Bohr model survives today for one reason. It is a useful teaching simplification. It is not what is actually happening inside an atom. Number 7. The quantum mechanical model. Electrons are not particles in orbits. They are probability clouds. In 1925 and 1926, Werner Heisenberg and Erwin Schrödinger, working independently with different mathematics, arrived at the model physicists still use today. Schrödinger built on a proposal by Louis de Broglie that electrons, like light, could behave as waves rather than solid particles. Schrödinger wrote an equation, now simply called the Schrödinger equation, that describes how the wave associated with an electron evolves over time. Solving that equation for the hydrogen atom does not give you an orbit. It gives you a wave function, a mathematical object that, when squared, tells you the probability of finding the electron at any given point in space. Physicist Max Born clarified what this actually means in 1926. The electron is still a particle in the sense that you measure it, you find it at one specific location, but before you measure it, it does not possess a definite location at all. It exists as a spread-out probability distribution, an electron cloud, occupying a three-dimensional region called an orbital, not a path, a shape. The regions where the electron has a meaningfully high chance, conventionally defined as 90%, of being found if you were to look. This is governed directly by the Heisenberg uncertainty principle, formalized in 1927. You cannot simultaneously know an electron's exact position and its exact momentum. Not because your instruments are not good enough, because the electron does not possess both properties with definite values at the same time. Measuring one property disturbs the other. Every electron in an atom is described using 4 quantum numbers: the principal number defining its energy level, the angular momentum number defining the orbital's shape, the magnetic number defining its orientation in space, and the spin number defining one of 2 possible spin states. No 2 electrons in the same atom can share all 4 numbers simultaneously, a rule called the Pauli exclusion principle. This single rule is why atoms build up in the specific structured pattern that produces the periodic table, and ultimately why chemistry has the shape and structure it does. This model matches experimental spectral data to extraordinary precision across every element, not just hydrogen. It has never been contradicted by experiment. It is also, by the admission of most physicists who work with it daily, deeply strange to actually visualize. Number 6. The atom is not mostly empty space. a common claim that modern physics rejects. You have probably heard this fact stated as though it's settled science. An atom is 99.99999% empty space. If you shrank the nucleus to the size of a marble, the electron would orbit at a distance of several kilometers, and everything in between is nothing. This description comes directly from the Bohr model, treating the electron as a tiny point particle at some specific distance, with vast empty gaps between it and the nucleus. Under the quantum mechanical model, this description does not hold up. The electron is not a tiny marble sitting somewhere specific in that gap. It is a standing wave, a probability cloud that fills the entire volume of the atom simultaneously. There is no empty gap between a point particle electron and the nucleus, because the electron is not a point particle sitting at a distance in the first place. Its wave function has some amplitude at essentially every point within the orbital's volume, including regions very close to the nucleus. Beyond that, quantum field theory, the deeper framework underlying all of this, developed through the mid-20th century, describes electrons not as particles occupying space between other particles, but as localized excitations of a field that itself extends throughout space. Under this view, an atom is filled, edge to edge, with electromagnetic fields, quantum fields, and the probability structure of its electrons. It is not full of solid matter in the everyday sense, but it is also not empty in the sense the marble analogy implies. The description that most closely matches modern physics is that the atom is a dense structure of interacting fields and probability distributions, not a wide-open space with a tiny hard nucleus rattling around inside it. Number 5. Inside the nucleus. Protons and neutrons are not simple objects either. Zoom past the electron cloud and into the nucleus itself, and the picture gets stranger, not simpler. Protons and neutrons, collectively called nucleons, are not fundamental particles. Each one is built from 3 smaller particles called quarks, bound together by the strong nuclear force. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Here's the detail that surprises almost everyone who first hears it. If you add up the measured masses of the 3 quarks inside a proton, you get only about 1% of the proton's actual total mass. 99% of a proton's mass, and therefore the overwhelming majority of the mass of every atom and every object you have ever touched, and your own body, is not the mass of the particles inside it. It comes from the binding energy of the strong nuclear force field holding those quarks together, converted into mass through Einstein's E equals mc squared. You are not, in the most literal physical sense, made mostly of matter. You are made mostly of the energy of a force field. The particles carrying that force are called gluons. Unlike photons, which carry the electromagnetic force but have no charge themselves, gluons carry a property called color charge and can interact with each other directly. This self-interaction produces a phenomenon called confinement. As you try to pull 2 quarks apart, the force between them does not weaken with distance the way gravity or electromagnetism does. It stays roughly constant or even increases the way a rubber band gets harder to stretch the further you pull it. Pull hard enough and the energy invested in stretching that bond becomes so large it spontaneously creates a new quark-antiquark pair out of the vacuum, snapping the connection into 2 separate particles rather than releasing a single free quark. No free quark has ever been directly observed, isolated, alone, anywhere. This is considered one of the fundamental confirmed features of nature. Number 4. The vacuum inside the atom is not empty. Virtual particles are constantly appearing and disappearing. Even in the spaces inside an atom that contain no matter at all, quantum field theory predicts something is happening continuously. The Heisenberg uncertainty principle, applied to energy and time rather than position and momentum, permits brief temporary violations of energy conservation, provided they are short-lived enough. This allows what physicists call virtual particles, particle-antiparticle pairs that spontaneously appear out of the vacuum, exist for an extraordinarily brief instant, and then annihilate each other and disappear, all without violating any conservation law overall. This is not idle theoretical speculation. It has directly measurable consequences. The Casimir effect, first predicted in 1948 and experimentally confirmed since, shows that two uncharged metal plates placed extremely close together in a vacuum experience a real, measurable attractive force produced by the plates restricting which virtual particle wavelengths can exist in the gap between them compared to the space outside. Inside a hydrogen atom, virtual particle interactions produce a tiny, precisely measured shift in electron levels called the Lamb shift, confirmed experimentally in 1947 and calculated by quantum electrodynamics to extraordinary precision, one of the most accurately verified predictions in the entire history of physics. The space inside every atom, including the seemingly empty regions of the electron cloud, is filled with this constant, frantic, and largely invisible activity, particles blinking in and out of existence continuously at every point in space, everywhere, all the time, including right now inside every atom in your body. Number 3. The measurement problem. Nobody actually agrees on what happens when you look. Here is the theory that sits underneath everything I already covered, and the one physicists argue about most. The Schrödinger equation describes an electron's wave function evolving smoothly and predictably over time, spread across multiple possible states simultaneously, a superposition. But the moment you measure the electron's position, you always find it in exactly one specific place, never smeared out. Something happens between the smooth wave-like evolution and the single definite measurement outcome. What that something actually is remains, after a full century of quantum mechanics, unresolved. The Copenhagen interpretation, associated primarily with Bohr and Heisenberg, holds that the act of measurement causes the wave function to collapse instantaneously and irreversibly into one of its possible outcomes, with the underlying probabilities given by the Born rule. This is the interpretation taught in most textbooks. It works perfectly for calculating experimental predictions. It does not explain what physically constitutes a measurement, or why observation specifically triggers collapse rather than any other physical interaction. The many worlds interpretation, proposed by Hugh Everett in 1957, rejects collapse entirely. Instead, it proposes that every possible outcome of a quantum measurement actually occurs, with reality itself branching into separate non-interacting universes for each outcome. Under this view, there is a version of you in a genuinely separate branch of reality who measured the electron in a different position than the one you observed. No collapse, no randomness, just continuous branching. The pilot wave theory, developed by Louis de Broglie in the 1920s and revived by David Bohm in 1952, proposes something different again. The electron is a real particle with a definite position at all times. It never stops existing as a point, but it is guided by an associated wave called the pilot wave that determines where it goes. Under this model, the apparent randomness of quantum mechanics is not fundamental at all. It reflects our ignorance of the electron's exact initial position, similar in spirit to how classical statistical mechanics treats gas molecules. All three interpretations, along with several others, including objective collapse theories and relational quantum mechanics, make identical experimental predictions for every test performed so far. There is currently no experiment that can distinguish between them. What is actually happening inside an atom at the deepest level, when nobody is measuring it, remains an open philosophical and physical question that the mathematics itself does not settle. Number 2. The shell model and the liquid drop model. Two different pictures of the nucleus. Both needed, neither complete. Physics uses two very different mental pictures to describe what is happening inside the nucleus, and switches between them depending on what needs to be explained. The liquid drop model, developed in the 1930s primarily by George Gamow and later refined by Niels Bohr and John Wheeler, treats the nucleus as a small drop of incompressible nuclear fluid held together by a balance of attractive nuclear forces and repulsive electric forces between protons. This model successfully explains why heavier nuclei can split apart in nuclear fission, the same way a large water droplet vibrating too violently will pinch off into two smaller droplets, and it correctly predicts the general energy released in that process. It captures collective, bulk behavior extremely well. It says almost nothing about the specific internal arrangement of individual protons and neutrons. The nuclear shell model, developed independently by Maria Geppert-Meyer and Johannes Hans Daniel Jensen in 1949, work that earned them the Nobel Prize in Physics in 1963, treats the nucleus completely differently. It proposes that protons and neutrons, just like electrons around the nucleus, occupy discrete quantized energy levels within the nucleus itself, arranged into shells. Nuclei with completely filled shells containing what are called magic numbers of protons or neutrons, including 2, 8, 20, 28, 50, 82, and 126, are measurably more stable and more tightly bound than nuclei with partially filled shells. This model explains patterns of nuclear stability, radioactive decay behavior, and nuclear reaction rates that the liquid drop model cannot touch. Both models are simultaneously used by working nuclear physicists today, applied depending on which specific nuclear property needs to be calculated. Neither is a complete first principles description built directly from the underlying quark and gluon interactions of quantum chromodynamics. That calculation, called ab initio nuclear theory, remains computationally extraordinarily difficult even for the fastest supercomputers currently operating, and is only tractable in 2026 for the very lightest nuclei. Number 1. What we still do not know: the proton radius puzzle and the limits of the model. Even the most basic property of the simplest possible atom, the physical size of a proton, has not been fully settled. For decades, physicists measured the proton's charge radius using two different experimental methods: scattering electrons off protons and measuring the energy levels of ordinary hydrogen atoms using spectroscopy. Both methods converged on a consistent value around 0.88 femtometers. In 2010, a research team led by Randolph Pohl used an entirely new technique, creating a muonic hydrogen in which the ordinary electron orbiting a proton is replaced by a muon, a heavier cousin of the electron that orbits much closer to the nucleus and is therefore far more sensitive to the proton's exact size. The measurement came back significantly smaller than the established value, a discrepancy large enough and precise enough that it could not be dismissed as ordinary measurement error. This became known as the proton radius puzzle, and it triggered a decade of intense investigation because a genuine discrepancy of that kind could have signaled the discovery of new physics beyond the standard model entirely. By the early 2020s, new extremely precise measurements using improved electron scattering and hydrogen spectroscopy converged toward the smaller muonic value, largely resolving the discrepancy as a result of earlier experimental imprecision rather than new physics. But the episode is a direct demonstration of something important. Even the exact physical size of the simplest possible atomic nucleus, a single proton, required over a decade of intense international effort to pin down with confidence. Beyond the settled parts of the puzzle, deeper, unresolved questions remain. Quantum quadrodynamics, the theory governing quarks and gluons, cannot yet be fully solved analytically. Physicists rely on massive numerical simulations called lattice QCD to approximate nuclear behavior, and even these remain limited for anything beyond the very lightest elements. Quantum gravity, how gravity behaves at the extraordinarily small scales inside a nucleus, has no confirmed theory at all. And the measurement problem discussed earlier remains completely open, with no experiment yet devised that can settle which interpretation, if any, correctly describes what is actually happening when a wave function becomes a single definite outcome. The atom is the most rigorously tested structure in the history of physics. It is also, at its deepest levels, still not fully understood. 8 theories and models. The Bohr model, the picture everyone learns first, and the picture that is wrong. The quantum mechanical model, electrons as probability clouds rather than orbiting particles, confirmed to extraordinary precision. The collapse of the empty space myth, an atom filled edge to edge with fields and probability rather than vast empty gaps. The inside of the nucleus, quarks bound by a force that gets stronger with distance, and a proton whose mass is almost entirely the energy of that binding, rather than the particles themselves. A vacuum that is never actually empty, filled with virtual particles blinking in and out of existence continuously. The measurement problem, 3 or more competing interpretations of quantum mechanics, all making identical predictions, none of them experimentally distinguishable after a century of trying. 2 entirely different nuclear models used side by side because neither one alone captures everything. And a proton radius that took over a decade of the most precise experiments in physics to finally pin down. Every atom in your body has been sitting there this entire time, doing all of this simultaneously at every instant without you ever noticing any of it. Subscribe to Cosmic Hives. See you in the next one.